Good afternoon. I want to go over a couple topics to do with experiments. By definition, an experiment has to have control. Control could mean a couple things. A control group is what it could mean, first of all. A control group is something to compare the treatment group against. You don't just want to give, if you're trying to see if a certain prescription drug works, you don't just want to give everybody the drug and, see if it works, because maybe the mind is having an effect. Maybe there's a placebo effect. You want to have something to compare that treatment group to. So that would be where a control group comes into play. But control can also just mean controlling the effects of irrelevant variables, making sure that you are controlling what is going on in the experiment. It needs to have randomization. That's where we randomly assign to the two different groups, to the treatment, to the control group, or to the two different treatment groups, reduces bias. And it must have replication, and that means repeating the experiment and using many individuals. We call it just anecdotal evidence if a drug, say, works for one person, or if some treatment has an effect on one or two people. That's only anecdotal. Replication means it works for many, many people. The other topic I want to focus on right now is the confounding variable. We were talking about this yesterday on the PowerPoint, and the definition of it, well, it must do two things. To be a confounding variable, it must impact the issue being studied. But so do lurking variables. But what really makes it a confounding variable is it must apply clearly differently to the two groups, or to one group more than another, or differentiate the groups. So yes, it must impact the issue, but it must apply differently from one group to the other. An example of that is right here we were talking about. And here we talked about what could be affecting the students and how well they do on a test. Well, there's many lurking variables. You guys mentioned IQ, sleep, study habits. But do we really know that the students in method A sleep better or worse than method B? Do we really know that the students in method A have higher IQs than the students in method B? And remember, we're randomly assigning. So that generally tends to evenly split the students in that category. But when you look at the teacher variable, there's a teacher doing this method for several weeks and different teacher doing this method for several weeks. Now again, the teachers may be both just great, but still it's a confounding variable because it could affect the results, and it applies unevenly to the two groups. So now we're confounded, or confused, in other words, as to whether it was the method that produced better results or the teacher itself. So these are the things we'd want to take care of. A confounding variable can render an experiment rather useless because we don't know what really caused the differences. And finally, a matched pairs design. This is considered by many to be the best experimental design that you could run. Why? Because it basically destroys just about all lurking variables. How does it do that? Well, you take your subjects, and instead of splitting them half and half, all subjects do both treatments, and you're comparing the results to yourself. So there's nobody more like you than you. Wouldn't you agree? So if I had you wear a magnetic bracelet to see if it reduced your arthritis pain, and I had you wear another bracelet, which you didn't know was a placebo bracelet, you were blinded, and we measured your pain from your arthritis, and I compared how you felt with the placebo bracelet to how you felt with the magnetic bracelet. Now all of those lurking variables, like family history or exercise or how well you sleep or your pain tolerance, those are pretty much they don't have any effect on us because you're comparing you to you. How did you feel with the magnetic bracelet? How did you feel with the placebo bracelet? Now we can make a more clear distinction on whether the magnetic bracelet really does help arthritis or not. A couple other things about this. You still need to randomly assign something though. What you do is you randomly assign the order in which each subject goes through this experiment. Half of the people will wear the magnetic bracelet. Now they don't know they have it on. We're going to blind it. Right? And then they'll have a washout period. That just is a period of time in between the two treatments. In case they were given a drug and it's in this treatment, you'd want to let it wash out of their system. But anyhow, half the people would wear the bracelet, have a washout period, and then wear the placebo bracelet. The other half would go in the opposite order. They'd go in this branch, and they would wear the placebo bracelet, then the washout, and then the magnetic bracelet. As you can see, we take every precaution to avoid bias in order to finally claim causation, to finally be able to say, guess what? Magnetic bracelets don't work. Now, quickly, double blind and placebo effect. We kind of mentioned it already. Single blind is when the subject doesn't know what treatment they're getting. Double blind is when even the researcher collecting the data doesn't know. Yes, even that could matter. If the researcher knew that these people here had nothing more than a placebo bracelet, which just means like it has no magnets, it has no cause or effect in it, then they might tend to bias, if they're interviewing them about their pain, they could have a bias on, well, I knew they had a placebo bracelet, so I'm not expecting them to have much pain relief. And so we don't even want the researchers collecting the data to know which group these people were in. Now somebody will know. They'll collect the data. This will be group A, and these people here will be group B. So then they can take this information about their pain and give it to the person who actually knows who was in what group. And there you have it. See you soon.